Okay, so let's start. We're happy to have Inbal Talgam-Cohen today, who is going to tell us about incomplete information, VCG contracts for common agency. Welcome, Inbal.
Hi, thanks so much. I'm really glad to be here. This is joint work with Tal Alon, Ron Lavi and Shamash. So Ron, I don't need to introduce. Tal and Elisheva are both students at the Technion. Tal is actually also now pursuing a military career, and I'm so glad she could join us. She's at Bad Echad, and I think she skipped Toronot Midbach to join us. By the way, you can also hear her giving a talk about this work at EC next month. Okay, so
I like your verb of pursuing.
Yes. Yes. By the way, throughout the talk, please feel free to jump in with questions and jokes and remarks. Okay, so I want to start kind of with a high-level view. So I think we're used to thinking of markets as allocating resources, goods, but actually when you look closer, you see that markets are used also to allocate effort. Okay, and by this I mean any situation where one party, a principal, hires another party, an agent, to perform some task for her, some task that requires effort, okay, costly effort. And let me show you a couple of examples. So, of course, online labor markets, this is where principals can hire a freelance agent to work on some project for them. Another example is a marketing agency, where you have advertisers that the marketing agency is bidding on their behalf for ad slots. An influencer can represent and promote several brands. Another example that I like is that even a major market player like Airbnb has some characteristics of an agent. Okay, in some sense, it operates on behalf of different market players. Bottom line of this is that agency or allocation of effort, incentivizing effort, this is prevalent in digital markets. Now, this motivates having a theory to underlie these applications, okay? So we already have a very well-developed theory for, or I should say both a theory and algorithmic theory even of resource allocation mechanisms. And I think in recent years, it seems that it would be a good idea to have a parallel for the allocation of effort. So there have been a few papers in this direction. I want to mention in particular Moshe's work, Michal and Noam's work on, I think this is the first instance I know of work that combines a kind of allocation of effort or contracts with the algorithms or algorithmic point of view. Okay, my co-authors Paul Duding and Tim Rothgarden and I have also worked on this, and there are actually a handful of other papers. I didn't write here everything, these are just examples. In this work, we're going to focus on finding a parallel to VCG. Okay, so this is kind of fundamental mechanism for resource allocation that achieves truthfulness, welfare maximization, and supports multiple buyers. And we want to see whether there's a parallel for research for effort allocation. And during the discussion, I think one of the interesting things that comes out is that algorithms play a central role. Okay, so it's not maybe it's not a coincidence that this question was open until now, was largely open until now. Okay, so I want to quickly give an introduction to the principal agent model, the classic model from economics for incentivizing effort. In this model, we have two players. Okay, this is just the most fundamental model. In our model, we'll actually have more than two. Okay, but here we have two players, an agent and a principal. And the model goes as follows. The agent is going to take, there's going to be an incentivizing mechanism, which is called a contract. This whole field is also called contract design. And there's going to be some costly effort that the agent performs. This costly effort results in a noisy outcome. And by noisy, I mean, if you think back to the labor markets example, so we have like a freelancer who's putting in effort. It could be that despite the effort, the project fails. And it could be that, you know, an agent that doesn't put in so much effort gets lucky and the project succeeds. Okay, so this is what I mean by noisy outcome. The principal gets value from the outcome. Okay, and according to the outcome, it pays the agent. Okay, according to the outcome and what is written in the contract. So this is kind of high-level view, and I want to specifically point out two ingredients that are really at the base of this relationship between a principal and an agent. They're really what drives this whole relationship. Okay, and these are the following. The principal is the better risk bearer. Okay, so the principal you can think as having, you know, deep pockets, being able to kind of take risks, having money and resources and so on. But then the agent is the one that's performing the action. Okay, and the principal who hires the agent to do some tasks, like if you're hiring a freelancer, you don't really observe every action that your agent takes. Okay, you kind of care about the bottom line. Okay, you're not able or not interested in seeing exactly what the agent does. You care about whether the project succeeds or not. Okay, so this is why I put this kind of screen in between the principal and the agent to, it's like a visualization of the fact that the agent's costly effort is not observed directly by the principal, only through the noisy outcome. Okay, and really without these two ingredients, this is what drives the whole contractual relationship. Together they form what's called the agency problem. Okay, and this means that we have one party who's taking the action. Okay, and we have another party who's bearing the risks, and the incentives of these two parties don't necessarily align. Okay, this is called the agency problem, and it's a super fundamental problem. It's underlies, you know, whole subfields of law, for example, and so on. Okay, so what do we want to do when we design contracts? Basically, we want to design payments or outcome-dependent payments, because all the principal sees are the outcomes, the noisy outcomes, and we want the payments to solve the agency problem for us. And what does this mean? This means two things. So first of all, remember that the agent is not a good risk bearer. Okay, so we never want to have the agent pay out of pocket. Okay, the payments are always non-negative. The money is only flowing in one direction, only from the principal to the agent. Okay, so this is kind of the answer, is the first ingredient of risk averseness of the agent. Okay, and the second one was hidden action. Oh, sorry, I want to mention that this is called limited liability, or LL in short, and I'll be using this a lot throughout the talk. Okay, so limited liability just means that the contractual payments are non-negative. And the second thing that the payments should ensure me is that despite the fact that the agent's action is hidden and not observed directly by the principals, it will maximize the objective of the contract. In this work, we are focusing on welfare. So we want the contract to maximize, we want the agent's chosen action to maximize welfare, even though nobody observes the action directly. Okay. Good. So that was the introduction to the fundamental economic model.
Inbal?
And now what, yes?
Hi, sorry, I have a few small questions. I'm less versed in the contract design. The welfare that we're trying to maximize is the welfare of the manager and the agent, or? Right,
exactly. So if you sum up the utility of all of the players, the principal and the agent, then this is the welfare. And I will show you, this is kind of only the introduction part, but I will show you the precise model, and I will define welfare. Okay, so
there will be some more formulated effort and so forth.
Yes, there will be. Okay. What do you mean? Do you mean whether
like we haven't defined what an effort is? Like what's the input and output? Like it's I could guess that the effort is the payment of the agent, and the money that the manager give him is the value, but I'm not sure.
Okay, you're
like what is the utility function of the agent? It isn't defined here, so I just want to make sure I understand.
Good. I will define all of these things. Let me say that the basically the utility of the agent, exactly what, like you said, it will be the whatever the principals pay minus the costly effort or costly action. Okay, but I will show you this in a minute. Good. Okay, so here is the model that our work applies to. It's by Bernheim and Whinston. And just like VCG auctions have multiple buyers, here we have multiple principals, okay, and a common agent that's working with all the multiple principals. Again, we have a hidden action. We have this screen between the agent and the principals. They can't directly observe the agent's action. Okay, I want to point out that interestingly, Bernheim and Whinston had another paper in the same year in which they introduced the same model, but with complete information, meaning that the action of the agent was observed. Okay, and this is of course less challenging setting, and questions there were resolved earlier. Okay, at least with a single agent. Okay. Examples of where we have multiple principals, the freelancer and employers, as we mentioned, manager and shareholders, regulator and citizens. Maybe another example that's closer to our kind of lives is a student and multiple advisors. And now when we have this common agency model, what do we want? Oh, sorry, I want to mention that in the digital market era, a lot of times the multiple principals have some platform, right? So when you have a freelancer on an online labor market, you have a platform like Odisk. And this might kind of coordinate the principals, and we're kind of gonna use this in some sense. Okay, so when you have multiple principals, this makes the problem, the agency problem more severe. Why? This quote is from Wikipedia, from the page on multiple principal problem, and basically more issues arise because the principals now have private information themselves, okay, and they're not coordinated in their incentives. So the setting is becoming more challenging because you don't only have hidden action of the agent, you also have hidden values of or hidden types of the principals. And what are these hidden types? These are the values that the principals attach to the outcomes of the agent. Again, I'll define everything more formally, but this is what you should have in mind. Two kinds of information asymmetries. Okay, one, information that the agent knows more, which is the action that he takes, and one that the principals know more, which is how much value the outcomes generates for them. Okay, and of course, if we only had the hidden values, the hidden types, we could do something, right? We have VCG in the auction world, and that maximizes welfare, and that's truthful, and that's great. But once we add in the hidden, the incomplete information or the hidden action of the agent, then things become difficult. Okay. And the way we want to address this is to design contracts for the common agency setting. Our approach is the following. We're going to solicit the principals' values for them, and we're going to use those to design the contract, these outcome-dependent payments that are supposed to address the agency problem. Okay? And what we want, the requirements, the design goals that we have in mind are the following. So for the agent, we still want the payments to be non-negative. We still want limited liability, and we still want welfare maximization to be the agent's best choice of action, even though we don't see the action. Okay, but now we have extra requirements. We want for the principals to have truthfulness and individual rationality, And we want this in dominant strategies. Okay, in this work, we focus on dominant strategies, just like VCG auctions. Okay, so here's an overview of our results. We define a family of contracts called incomplete information VCG, or IivCG for short. This is the unique family of contracts that achieves truthfulness for the principles and welfare maximization by the agent. We will characterize the payments or the transfers from the principals to the agent. And you'll see that in this characterization, we have parameters, H, L, and W. L is the principal, okay? And this is similar to standard VCG, right? If you know, if you remember in VCG, we have this exactly, even it's defined many times as HL, it's denoted, sorry, many times as HL. And then it's instantiated by Clark pivot rule. We'll have the same thing for IivCG family. And then ideally, we would want to select HL and WL to ensure the two requirements, the two additional requirements of limited liability and individual rationality of the principles. Okay.
But quick question: is there an issue of budget balance here, or?
Excellent question. Yes, this is exactly what will come up. So as you kind of guessed, number 3 is not possible to achieve. The issue is very related to budget balance. I'll try to say why it's even more severe than budget balanceness. Okay, I'll show you an example of why we think it's even more severe. So limited liability and individual rationality are incompatible. This will kind of be the driving, the motivation behind our algorithmic approach. Okay, so the main algorithmic results are 2 algorithms. One of them will get a common agency setting and determine whether it has a contract that can achieve both limited liability, both has non-negative payments and individual rationality for the principals. Okay, and the second agent, the second algorithm, if such a contract exists, it will kind of compute it on the fly. Okay, the principals will report their values, and it will give back the vector of transfers of payments. The algorithms are LP-based, and they run in polytime. So this is kind of all I wanted to say for the introduction. Now I will kind of show the model with examples. I'll define IivCG and also show the algorithms. So it's a great time for questions.
So Inbal, if it doesn't exist, what do you get?
If it doesn't exist, then the algorithm that checks whether it exists or not will return that it doesn't exist. And we did not address this further. I think this is
so you didn't try to approximate it.
Exactly. I think this is the next obvious, or not obvious maybe, but I think it's a great suggestion, and I think it could be really interesting to see what you can get. So you would want to approximate welfare, maybe give up some welfare, but still get the good properties. I think this would be a very nice research direction.
Inbal,
that if it doesn't exist, it's accounted for as 0 in terms of the utility of the principle. Right?
Sorry, I couldn't hear the question.
Ran, you are completely unclear.
Can you hear me better? Can you hear me?
Yes.
Slightly better, yes. Now I hear you, yes.
I'm saying, given your answer to Moshe, I'm assuming that you account for the principal's utility as being 0 when it doesn't exist, right? So that would be probably your modeling assumption.
Yeah, kind of. They're like nothing.
Because they assume it could not, so they give some probability that it doesn't exist, and then what happens then should be factored into their strategic considerations. So in order to ignore that, my suspicion is that it should be 0.
So that connects to
that is not true, because it really depends on the probability that it would exist, maybe had they reported something else. So this is a bit tricky in terms of.
So we addressed this because
can I because I also want to clarify something. When you say exist or not, at what stage? At the ex-ante stage before they get the values, or at the interim stage after they know the values? That will also clarify Ran's question, I think.
Yes, I agree. It's at the ex-ante stage.
So the existence stage is the ex-ante stage.
Yes.
Okay, so then Ran is correct to ask what he asks.
Yes, yes. Let me. I think I should show you the model, and then it will become clear. No, and I think that answers Ran as well, because now it doesn't right. So for anything they would bid within their domain, it's truthful. Let me show you actually the formal model, and then we can discuss again. Okay. So here's the formal model, and it's just the model of Bernheim and Whinston. It's parameterized by the number of principles n, by the number of actions available to the agent q, and by the number of possible outcomes that can come out of the agent's action m. Okay, and every action that the agent can take among the q possible actions has a certain cost, psi I, for the agent. Okay, we assume that there's always an action that has zero cost, so the agent can always just kind of choose to rest and not put in effort, and this kind of ensures participation on the agent side. And then once the agent takes an action, it induces a distribution over the m outcomes. Okay, so this is kind of, if you think of two outcomes, success and failure, so different actions have different probabilities of success. And we're going to denote the distribution by f given ai if the action is a sub I. Okay, now the principles have domains of valuations. For principle L, this is denoted VL. Okay, we assume that they're convex for computational reasons. Okay, we want to have, like, say, a polynomially sized polytope maybe, or at least some kind of membership oracle. This is why we assume convexity. And I want to stress that this domain, every evaluation in this domain, what kind of object it is, it's just like a mapping from any outcome that the agent can achieve to a value for the principal. Okay, so this is the setting. This is publicly known. And then this is like the ex-ante stage, as Sergio was saying. But then once the evaluations are realized, they are private to the principals, and the agent the action that the agent will choose is also private knowledge of the agent. Okay, let me show you a picture so this becomes more kind of concrete. So here's the setting. I'm showing you it with the private valuations of the principals. On the agent side, I have these Q actions that the agent can choose upon, and the actions can lead to M outcomes. Sometimes this is drawn as a matrix. Here we draw it as a complete bipartite graph. And you can see that each action has a cost for the agent, psi I, and each action leads to every one of the outcomes with a certain probability, where we denote the distribution by F sub AI, F given AI. Okay, that's the agent side. Now the principal side, they have n principles, and each one of them has a vector of values, one for each outcome, and these vectors come from the domain, the publicly known domains of the principles. Okay, so this is the setting, and now I can define welfare. Okay, so
just a quick question: is there like a prior over these valuations?
No, there's no prior in this work. In this work, we don't have a prior. I think that's also maybe a way to address this non-existence sometimes of good solution. Yeah. Okay. Great.
So you want a dominant, something like a dominant strategy kind of result,
yes,
not a Bayesian, but dominant strategy, no matter what the n tuple of valuations is.
Yeah. Yeah,
Okay.
whenever the valuations, they have to be in the domain, right? But other than that, no matter what they are, we want the principal to be able to tell the truth about her valuation vector and get the best possible expected utility. And moreover, it should be non-negative. This is individual rationality, okay? And I stress that anytime I say expected in this work, I mean, it's not like Bayesian over any distributions of valuations. What is random here is the outcome. Okay, so anytime I say expected, it's over the random outcome of the action. Okay, so here's what I mean by welfare. So if you fix a valuation profile V, okay, fix these V's of the principles, then the welfare is going to be the sum of expected value, sum over all principles of the expected value to principal L that playing action AI achieves, okay, minus the cost of this action to the agent. Okay, and I wrote this down using the notation that we introduced. It's you can see the sum over the principles, you can see the expectation over the random outcome, and the values that are reported by the principles, minus this tie AI, which is the cost for the agent. Okay, and another piece of notation is A star V will be the welfare maximizing action. Okay, so here's our first example. In this example, it's kind of a simple example where the agent has two possible actions, either resting or working. Okay, the cost of resting is 0 to the agent, the cost of working is epsilon. And the outcomes are either fail or succeed. And I'm assuming that if you put in effort, you're guaranteed to succeed. But if you rest, then you might get lucky with probability half and succeed. And then with probability half, you fail. Okay. In this example, let's say there are two principles. They both have the same domain, R2 non-zero values in R2. And let's say that they have the same value, which is 0 for failure and 3 epsilon for success. Okay, for each one of the principles. So just to kind of see what the welfare here is, you can see that if the agent rests, then with probability half, we will get 3 epsilon. So that's 1.5 epsilon times 2, because there are two principles and no cost. So the welfare is 3 epsilon. And if the agent works, then you get 3 epsilon times 2, which is 6 epsilon. And there's a cost of epsilon for working. And that means that the welfare is 5 epsilon. Okay, so here in this example, the welfare maximizing action is working. Okay. So now we have the setting, we understand what welfare is, and now what is the game? Okay, what's a contract and what is the game? So in the game, the principals report their valuations, and these valuations are used to induce a contract, which means a profile of transfers, one kind of vector of transfers for each principal, okay? And the principal has a transfer that is dependent on the outcome, okay? TLVO is the transfer of principal L given valuations V when the outcome is O. And it has to be non-zero, it has to be non-negative, and this is the limited liability that we require, okay?
By the way, here it will be suffice to get individual limited liability, what you call, on average, because the agent could say, for every action, I don't know what the signal is, but I want my average to be greater or equal 0, which is a weaker condition, and maybe that will help for existence. I don't know, just asking.
Yeah, so no, we require that for every outcome, the transfer.
Yeah, I know, I understand. I'm just saying that it will be interesting to see whether relaxing this to require the greater or equal 0 on average for each action. So it's for each action, the average over O should be greater or equal 0. It's a relaxation of the problem. Whether this helps or not, I don't know.
That would be very interesting. My guess would be that it would help, because I feel that this is. I also feel it's a fundamental requirement. Okay, that the fact that actually I think I have a slide on this. Okay, so let me leave it. Let me leave it for.
Okay.
What I thought you were going to say.
I want to mention that it won't help. Our lower bound is for all the principal's payments. Inbal will get to that later.
Okay, yes. So Tal is answering what I thought you were going to answer. You were going to ask, sorry, which is if you sum up over all the principals and ask that that is non-negative, this doesn't help. Okay, but the definite picture entirely, if you, oh, sorry about that. Okay, it definitely changes the picture entirely if you ask that only on average over the random outcomes, things are non-negative.
Maybe the trivializes the problem and it makes it into a one-dimensional problem that somehow only the expected outcome matters, and maybe what I asked becomes a triviality. So an uninteresting triviality where I think the number of outcomes becomes one and everything is just you look at the expected outcome and that's it. I don't know, maybe, yeah. But it would be interesting if that's a difference. That's because then one can put the finger on where the non-existence comes from the multi-dimension on the number of outcomes.
Great. Okay, so okay, where were we? So the the reports induce a contract. Now the agent has the contract in front of him, and he looks at the contract and he picks the action that maximizes his expected utility. Is the sum of expected transfers from the principal to the agent for taking this action minus the cost of the action. Okay, so he looks at this kind of utility, expected utility for each one of the actions, and he rationally chooses the one that maximizes his utility. And we want it to be the one that's maximizing welfare. Okay, once the agent chooses the action, we realize the random outcome by picking it from the distribution that is associated with the action. And then the principal transfers, each one of the principals transfers TLVO to the agent. And let me show you this in the picture. So we have the principals. They're reporting their values, and this induces the contract. Okay, and the agent looks at the contract, picks the utility maximizing action, and the random outcome is realized, and then according to the contract, the principals pay the agent. Now, I want to compare this kind of contract game to the mechanism design setting that we're used to. So in the mechanism design setting, like VCG setting, we also have players with vectors of valuations. They report it to the mechanism, and this kind of gives the social planner the different values for different alternatives, which could have a social cost psi I for alternative I, and the social planner will pick the welfare maximizing action. Okay, so you can notice that we don't have this whole part of once an alternative or an action is picked, some random outcome is realized. Okay, this is missing from the mechanism design setting. And now I'll show you in the example what difference
I think that, I mean, I understand what you're saying, but I would not say that is missing from the mechanism design. The mechanism design depends on the problem. You have a problem where you observe the A's, and that's what you have now, or you have a problem where you only observe the O's, and that's what you had on the previous slide. That's different. It's not a difference between mechanism design and not mechanism design. It's mechanism design for two different problems.
I agree with you. I'm using mechanism design here in a very limited sense. Some people, I know that a lot of people say mechanism design and they do mean contracts and auctions, and I agree. Okay, great. So let me show you this in the example. Okay, I'm looking at the same example that we had before, but this time I am instead of looking at two principles, let's even make it simpler and say we just have a single principle. Okay, the same valuation domain and same values as before. And now the welfares are a bit different. It's only 1.5 epsilon for resting and 2 epsilon for working. Okay, because we just have one principle, but still working is the welfare maximizing action. Okay, in the mechanism design version, this is what I meant by this part kind of being missing. We just don't have that part. Okay, we don't have that part. You have two social alternatives of either resting or working, and they have like social costs, 0 or epsilon. And what I want to say is that you have a solution to this, a simple solution to this that is achieves optimal welfare, and you can just kind of price the option of working at epsilon. Okay, and if a principal kind of comes and needs to choose one of these alternatives, then this price makes the principal internalize both the costs and the values, and the socially efficient action will be chosen. Okay, and I want to show why even in this super simple example, if you do have the contract design part, it becomes more complicated. Okay, the contract design version is more challenging. Let me show you this. So if you do have this random outcome, and that's all you see, and that's all you can pay for, what could you do? Here's a first attempt. Okay, and kind of you might be attempted to try. Just pay 0 for failure and pay epsilon for success. Okay, this is the contract. What would the agent do? The agent notices that if the agent decides to work, then her cost is epsilon, her payment is epsilon, so her utility is 0. But if the agent decides to rest, there's half a chance that she will get epsilon. Okay, so her utility is high, it's non-zero, and she will choose to rest. So this is not socially efficient, and that's not what we want. Second attempt is the following. Let's try to offset the fact that we gave epsilon even with probability half even for rest by giving -2 epsilon for failure. Okay, charging 2 epsilon for failure, and this would solve the problem. This was definitely.
I thought it's forbidden.
Yeah, this is exactly my point. So this would solve the problem in terms of maximizing welfare. The agent is now incentivized to maximize welfare, but as Sergio immediately noticed, it's forbidden, right? We're not. It doesn't really happen that you have some freelancer and you charge them for failing. Okay, it's very uncommon for a freelancer to be paying the people who hired him. Okay. So to summarize the design challenges, we have the challenges that come from the fact that common agency is within mechanism design and has hidden types. Okay, mechanism design here in the limited sense.
Inbal?
Yes.
So would it make sense to just do a shift until it reaches 0?
Right. So we still want to be IR. You still want to be individually rational. So this is exactly the tension. Great. This is, yeah, this is precisely the point that this is exactly what makes individual rationality clash with limited liability. Okay, so I'm just.
Except that I think you don't need, you need 0 to epsilon would solve the problem, no? Not the difference doesn't have to be 3 epsilon, only 2 epsilon, if I'm not mistaken, in my algebra.
Okay, I don't want to spend too much time on kind of looking at the algebra, but I can tell you that we can prove that no contract is both IR and LL and reaches all of the welfare maximizing and truthful for this setting. Okay, so this is
with a single principle. With a single principle.
Even with a single principle, exactly. This is important because budget balancedness, it's related to the fact that budget balance causes problems, but here, even with a single principle, there are already problems. Okay, and the problems come from the fact that we are combining hidden types with hidden action. Okay, let me quickly move on because I don't want to run out of time before I show you even what IivCG is.
Sorry, just understand, you have to embed this in a rich set of valuations. I mean, what you showed us up to now doesn't say anything. To get impossibility is to take the 0, 3 epsilon valuation vector and embed it into a bigger set, what you call script V of valuations, and then you are going to get impossibility. Up to now, there is no impossibility in what you showed us.
Yeah,
just to make it clear. Yes.
So in this problem, I did mention that the evaluation domain is.
Oh, I see. It's R2 plus. Okay, it's R2 plus. Okay, so if you take all possible valuations, then yes. Okay, but there are other subsets that include the 0, 3 epsilon, for which you do have possibility, of course.
Okay, great. So we are going to use a tool called Contractible Contracts, and we use this to design the IivCG family of contracts. Very quickly, what is a contractible contract? I'll say what a non-contractible contract is, and I'll say it quickly because it's stuff you know from auctions, okay? So non-contractible contracts is just like first price auctions. Basically, you get the reports from the principals, and what you make the principal pay for outcome O is her bid, okay? It's the value she said she has for outcome O, okay? So exactly like in auctions, it's non-truthful, and we can actually quantify how bad this is. We look at the equilibria and we use price of anarchy and price of stability analysis, and we can show that there are settings for which these prices are not good. Okay, so for price of anarchy goes to 0 even, and price of stability goes to half. By the way, we don't know if half is tight, but there are also the issues of how you arrive at equilibrium and so on. So this motivates looking beyond that, looking at contractible contracts, by which I mean that the transfer is can now depend not only on what you said and what you bid, but also on the bids of the others, also on the value reports of the others, okay? And this is really a strong tool because it makes us go from like first price to beyond first price. So just like in auctions, it's much more powerful. This is by Peter Sintez and Elisheva and Ron were, I think, the first to notice how powerful this can be for contract design in the complete information setting, okay? So this is a great tool. It enriches contract design. And now let me define a family of contractible contracts that we call IivCG. And a contract will be in IivCG if the following two conditions hold. So for every value report of the principals, the agent should choose to maximize the declared welfare. Okay, so should choose the action that maximizes the welfare according to this report. And the second condition is that the principal's expected transfer for this action, for this welfare maximizing action, is going to be HL, some function HL of the others' reports, of the others' bids. This makes it contractible. And minus the others' contribution to the welfare. So if this looks familiar from VCG, it's exactly VCG auctions, okay?
And Inbal, what about computational issues here?
So here we don't have computational issues. I should have mentioned it when I showed you the definition of the welfare, but I mean,
it's
the
all
value.
polynomial.
Exactly, it's all polynomial. In this particular setting, I think it's an interesting open question. What if the valuations are more complex? Okay. So even from this, okay, I defined here a family of contracts. I didn't tell you what HL is. I didn't really even tell you what the transfers are, just what the expected transfer for the welfare maximizing action is, okay? But even from this, you can already show that IivCG contracts are truthful and that they're welfare maximizing. So from now on, I used B for reports on the previous slide. From now on, I'll be using V because these contracts are truthful. Okay. So we already have.
What is off? You said something that the computation is offline. What is offline?
Not offline. I said that the computation is polytime.
Oh, polytime. You said. Okay, sorry, I misheard. Okay.
Okay, so we already have truthfulness and welfare maximizing, and the two other requirements are. Oh, sorry. I should say another thing we know about this class is that it's unique, and this is very, you can kind of massage a classic result of Holmstrom to show that this is the unique class of contracts that we should be looking at if we want truthfulness and welfare maximization. Okay, so now I'm going to show you, I want to show you a characterization of the payments. So far, I just said what the expected payment is for the welfare maximizing action. I want to show you now what the actual payments are. So you get an outcome, what do you pay? I need the following definition. So let's look at a valuation report V, and let's look at all of the possible contracts, all of the possible transfer vectors that could incentivize the agent to take the welfare maximizing action, and all of the ways there are to split this these transfers among the principals. Okay, so W1 to Wn are all the ways to split this among the principals. Now I can show you the characterization. Here's one of the lemmas that we have in the paper. So a contract is an IivCG, has those two properties I showed you before. If and only if, for every valuation report, there is W, okay, this vector of transfers that incentivizes the agent to choose the welfare maximizing action. And there's a way to split them among the principals, and so that the transfers are as follows. They're that HL that we showed before, minus welfare from the welfare maximizing action is the valuation where WL, plus WLFO. Okay, so the details here don't matter so much, but what matters is to see that there is a characterization of the payments that depends on two parameters, HL and WL, okay? And we ideally would want to find such parameters so that the contract is IR plus LL. This is not always possible. The idea will be to identify the settings for which it is possible and to get an algorithm to compute HL and WL. Okay. You might be thinking, why did I bother with HL, right? In VCG, you kind of almost automatically apply Clark's pivot rule, and you actually use the following HL, the HL that assigns the optimal welfare without a principal L, okay, which makes the expected transfers of the principals be exactly their externalities, okay? So this is definitely the first thing that we tried. And it gives a subclass of IivCG contracts that we called auction-inspired IivCG, okay? Unfortunately, as I kind of told you up front, it's not going to work for all of the settings, okay? So they are interestingly always IR, they're always individually rational for the principals, because just like in standard VCG auctions, the principals' expected utilities are their contribution to the welfare, and so they're always non-negative. But you don't always have limited liability. Let me actually skip the intuition of why and just jump to the example. This is the same example that we showed before. And this contract that we tried, paying epsilon for success and charging 2 epsilon for failure, that's exactly what you get if you apply this method of auction-inspired IivCG to this particular setting. Okay, so it gives you, you can see it gives you a contract that has individual rationality but does not have limited liability. Okay, the payments here are negative. Okay, and furthermore, we show in the paper that for this setting, no IivCG contract has the 2 properties of individual rationality plus limited liability. Okay, and we showed that IivCG family is the only one that is interesting. Okay, it's unique in welfare maximization and truthfulness. Okay, good. And this is the slide that I was looking for to answer Sergio. I think it answered Sergio's question. Okay, so at this point, you might be maybe asking yourselves why you're insisting so much on limited liability. Okay, if it makes our life so, I mean, it looks like such a natural class of contracts, right? And just this pesky limited liability issue. So maybe it's not so important. So please notice that if you don't require limited liability, you have a trivial solution. You can just kind of sell the project, okay, to the agent. And what do I mean by sell the project? You look at the maximum welfare in this setting, and you tell the agent, listen, you want this project? Okay, just pay me the maximum welfare, pay me 2 epsilon in this example, and now do your thing. And then of course the agent will take the welfare maximizing action and extract the welfare from the project. So this is an optimal solution, but it's trivial and it's against the whole nature of contractual relations where the agent exactly does not want to buy the project, does not want the risk involved in owning the project. Okay, good. So we have this trade-off between individual rationality and limited liability. We have a subclass of IivCG contracts that gets you IR, not an L. In the paper, we show a parallel subclass that gets you LL and not IR. Again, what next? So I will probably only have time to kind of present at a very high level the approach, but the idea is to look, instead of at classes of subclasses of contracts, we will now look at common agency settings, and we will look at every setting, and for these, we will try to see which ones do have IR and LL IivCG contracts, okay? And we know some examples where it doesn't exist, right? We saw that super simple example where I told you that it just won't work, okay? And here I give an example for which we know it does work. So any setting with values in the range of 1, 2, we can show an IivCG contract that is IR and LL does exist. And we can now try to approach this.
Well, what's a normalization? What does 1, 2? What's normalized here?
Yeah, this is not normalized. Yeah, this is for if you have a setting in
scale. Can't you scale this interval as much as you want?
That's.
You cannot scale I mean, no, you cannot scale you can't scale it.
Because you have the 0 point for limited liability?
Because I have, sorry? I didn't hear.
Because you have the 0 point for limited liability, is that what?
Yes.
I'm missing something. So what is fixed here? The costs, the size.
Let me be more general. So any setting with values in A and B such that B minus A is greater or equal than A. Okay. I don't want to go too much into this because I have, I think, only a few minutes. I want to just show you the slide with the algorithms. But yeah, this is, I just wanted to give, one example where it does hold that there are IR plus LL IivCG contracts. We have additional examples in the paper. Okay, in particular, these examples where the price of anarchy and price of stability of the first price contracts are very high, we can show that they do have IivCG contracts, which are IR and LL. Okay, so quickly, I want to show you the algorithms. Let me just kind of open up this slide. What we do is to give an if and only if condition for the existence of IR plus LL IivCG. Okay, this is a condition that applies to common agency settings. And then we have two algorithms. Okay, algorithm 2 gets a common agency setting and returns in polytime whether or not an IivCG contract that is IR plus LL exists. Okay, and algorithm 1 gets as input a common agency setting and a bid profile of the principals, and it gives me as output the vector of transfers of the principals for all of the possible outcomes. Okay, so both the condition is polytime verifiable, that's algorithm 2, and the fact that there's existence if this condition holds is constructive, and that's algorithm 1. Okay. So I will show you the if and only if condition.
So the transfers depend only on small v and not on the set big V. Is that correct? Because that's what algorithm 1 apparently does.
Sorry, can you ask that again?
I mean, the transfers depend only on the realized small v vector and not on the domain big V.
No, algorithm 1 does get the common agency setting as an input. It does have the setting as an input.
Oh, so the big V does enter there.
Yeah.
As well. Okay.
Okay. Okay, I think I have time just to show you the condition to make it less mysterious. Okay, so before I show you the condition, here's a lemma. Okay, if you fix the common agency setting, and you have a contract T from the class IivCG, okay? If you know it's IR plus LL, then you know that for every V, okay, the total expected transfer to the agent for taking the welfare maximizing action is sandwiched between some lower bound and some upper bound, which we give in the paper, and I have slides on, but probably I won't be able to show you, okay? And from this lemma, we can induce the following if and only if condition. Oh, sorry, I should say that the lower bound comes from limited liability, the upper bound comes from individual rationality. Again, from this lemma, we induce the condition that it turns out that if for every valuation profile in the domain, the lower bound is lower or equal to the upper bound, then there exists an IR plus LL IivCG contract and vice versa. Okay. So the upper bound and the lower bound are here in the slides, which I'll make publicly available. I have also some details about the algorithms showing why they're polytime. I think I should skip to the summary. The key takeaways, I think, from our work is, first of all, the power of contractible contracts. And I think this is something that was actually recognized by Elisheva and Ron, but I want to stress it here because it's such a powerful tool, and I'm excited to see, what other results it will lead to, because the literature was really kind of focusing and obsessing about first price contracts. Second takeaway is that even with a single principle in the common agency setting, there's an IRLL trade-off. Okay, and the third takeaway is that you can algorithmically address this trade-off. First of all, you can identify which kind of settings will have a good contract, and then you can, once you've identified this, you can implement this contract on the fly, so we can get the reports of the principals and return their transfers to the agent. Open directions. The first thing is what we already discussed, following Moshe's question. Second one relates to Michal's question. I think revenue maximization could be interesting. We don't even really know how to define revenue, I should say. It might be related to like platforms and the revenue that platforms can make from kind of coordinating different principles. And then I think it's also interesting to think about decentralized processes that might lead to welfare maximization and kind of VCG-like contracts without the need for a centralized platform. Okay, and very quickly an ad. So thanks so much for coming to this talk, even though it's a day of really interesting talks, and this is the schedule of ComSoc, which starts, I think, straight after this seminar. Yes, I'll definitely be in those talks. Okay, so maybe we have like 1 minute for questions, or I don't know, Sigal and Moshe, you should say.
Yeah, sure. Any questions? Thanks, Inbal. Yeah, this was great. Any questions?